What's up, CoderByte? Welcome back to another data structures and algorithms video. I had a great time preparing this week's problem. It's part riddle, part math equation, so super fun to think about, less fun to actually receive in an interview. I did receive a version of this at a real Facebook interview that I had. So without further ado, let's jump into this awesome classical interview problem. You have two glass balls and a building that has 100 floors. Using the glass balls, determine which floor is the highest floor a ball can be dropped from without breaking. Note, you can break both balls in the process as long as you can determine the answer. So this is one of those problems that is, I think, a classical interview problem. It doesn't really involve code. It's kind of a logic problem. Someone who doesn't know anything about coding might be able to solve this, right? It's something that you have to use your brain to kind of figure out, okay, there's a building, 100 floors, two balls. How am I going to go about, doing this? So I think a really useful tool and a good method for solving any interview problem, especially in those first 5 to 10 minutes when likely you're full of anxiety and just kind of the thoughts in your head are, I can't do this, I don't get it, this is too hard. I don't know if that's anybody but me, but maybe you relate to that. Often it's useful to break the problem into a smaller problem, a simpler subproblem, and brute force it, right? What would you do if you could simplify this and then you had to solve it without any fancy algorithm? So I think for this problem, a really useful question to ask yourself at first is, what would you do if you only had one glass ball, right? You have a building, you have one glass ball, and you have to figure out what is the highest floor that I can drop this from without breaking it. Personally, I would probably take that ball, I would start at that first floor, and I would drop it, and I would see, did it break? If not, great, go up to the second floor, try it again, right? And you would continue doing that until the ball broke, and that would be your answer, right? So that's a great answer. It works. But in this case, the worst case scenario is that the ball breaks at floor 99 or 100, right? And you have to drop it at every single floor leading up to that worst possible case, which is a lot of times. That is an expensive operation to actually climb all 100 floors and test each one individually. The other thing you can then remember is that you have two balls. So there must be some faster way that you could do this, right? Using that second ball. But you will, in an interview, get points for getting an answer. It's better than getting no answer. So that's a great way to kind of start you off in an algorithm. Let's take a simpler case, solve for that, and then go from there. So this is just kind of some illustrations for you that you go to each floor until it breaks, and when it breaks you have your answer, right? Okay, you have two balls, right? So we can go about this in a binary way. What do I mean by that? If you think of the algorithm binary search, how that works is it divides the array or the whatever you're searching through into two, and thereby you can narrow it down to a subset, right? Either the first half or the second half. That's how binary search works. You continue to divide in two until you find your element that you're looking for. So we can do a similar approach here. We can actually divide this building into two different sets, right? Floors 1 through 50 and floors 50 through 100. If we drop the first ball off of the 50th floor and it doesn't break, then we know that the answer is in that top half. It's in the 50th to 100th range, right? If it does break, we know that it's somewhere from the 1st to the 50th. We can then go to floor 75, divide in half again, and we drop ball 1 again. In this example, ball 1 breaks, right? That's what that red arrow is indicating. So we drop the ball 1 from 75 and it breaks. We now know that our answer is between 50 and 75 as opposed to 75 and 100, right? We can then take our second ball and do the naive approach, right? That's what we just did with the first, pretending that we only had one ball. And we can drop it at every single floor from 50 to 75 where we know the ball broke, right? And oh, it broke on 52. We have our answer, right? So let's talk about, how does this compare, right? In our worst possible case, the first ball drops one time, right? It breaks at floor 50. We can't divide it any further because now we have to take our second ball, because our first ball is already broken, and drop it at each floor from the first floor to the 50th floor until it breaks again. If it breaks at 49, our worst case is that we had to drop that second ball 49 times, plus the first time, which was our first ball. So that's 50 times. It's way better than dropping it 100 times, right? If we were going from, let's say, 0 to 100 with just one ball, we've drastically improved. But it's not great, right? So how can we make this algorithm just a little bit better? What if we skipped less floors with that first ball, right? Because if we skip 50 floors and it's in that first 50 set, we know that because the first ball breaks, we have to skip a lot of floors with the second ball in the worst case scenario. So maybe we can minimize that, right? We can skip less floors with ball one. So let's see. We skip 2 floors, right? Let's really drastically lower it and see what happens to our numbers. This is another tip for interviews, by the way. Try a bunch of stuff, right? Because at the end of the day, what the interviewer is looking for is your thought process. They want to know, is this person good at solving problems? Are they enjoyable to solve problems with? And if you don't know the answer, often if you're just curious and you just try a bunch of stuff, sometimes you'll surprise yourself and actually find the answer. Good tip for you. Anyway, so let's try and skip just 2 floors with that first ball and see what happens to our worst case numbers. So we skip 2 floors with ball 1, we're good. Skip 2 floors again, floor 4, ball 1 is still there, still intact. Great. We do that until, let's say, floor 98, right? And finally, we get to the 100th floor and our first ball breaks. So that's great, right? Because now we know that it's somewhere between 98 and 100, right? So it's either 99 or 100 is our floor that's the last floor that we can drop from, the first floor that it will break from. So we drop it on floor 99 with ball 2 and it breaks, right? Excellent. So our worst case numbers. Ball 1 drops 50 times, right? Because we basically skipped 2 each time. And the second ball drops 1 time, breaks at 99. Okay, so that's not great. It's not better than the binary approach for worst case scenario, right? But it gives us something to compare to. So we can see what's happening to our numbers as we drop these balls. So let's compare our worst cases. When we skipped 50 floors with ball 1, our cases were our amount of times we dropped the ball were we dropped once for the first ball, right? That was the worst possible case. And the second ball we dropped 49 times because we had to drop it on every floor from 1 to 50 and it broke on 49. That's our worst case, right? What happens when we skipped only one floor with ball 1? So we dropped ball 1 50 times, right? It broke on the 100th floor. And the second ball only had to drop 1 time. It broke on the 99th floor. And remember, we only have to drop it that 1 time because if it doesn't break, we know that the answer is the highest floor is 99 as opposed to 98, right? Because it broke on 100, it didn't break on 99, so 99 is our highest, so that would be the same. Okay, so if you look at these numbers, they're inverse, right? When we skip a lot of floors, the first ball we drop a lower amount of times, and the second ball we drop a higher amount of times in our worst case. When we skip one floor, the first ball drops a lot of times, but then the second ball drops less times, right? So the lower the number of drops the first ball takes, the higher the number of drops the second ball will have to take in the worst case scenario. The higher the number of drops the first ball takes, the lower the number of drops that second ball will have to take. They're inversely related. So maybe we could take advantage of that. So can we balance this out so that we make a similar number of drops with both balls, right? In our other scenario, we were kind of at either ends of the spectrum and it ended up evening out. It was the same, right? But maybe we could bring them both towards the middle and then we can get a lower number of total drops. How can we do that? Let's try skipping 10 floors at a time. And again, this is a good way to just test stuff out, right? So we're just picking 10. So we drop with ball 1 and we go to floor 10 and it doesn't break. We're good. Go to floor 20, go to floor 90, right? Skipping 10 floors at a time. And it breaks at 100. And then we drop from 90 to 100 with that second ball, 91, 92, all the way up to 99, right? Because this is our worst case. So we dropped the first ball 10 times, right? We've divided it into 10. And we've dropped the second ball 9 times. So that's for a total of 19 times. That's way better than anything we've gotten so far. So I think we're on the right track, right? So the interviewer is pleased and says, okay, good job, Elizabeth. Like, yeah, excellent. You cut it down drastically. However, you kind of picked 10 randomly. Why did you pick 10? And also, there's a better answer. There's always a better answer. I just whispered that there's always a better answer in case you didn't understand that, because that's always how it feels with these problems. But anyway, so we got 19, right? And we're trying to figure out, how do we pick that number? How do we get that magic skipping number? And how can we make this like an algorithm that we can apply for different amounts of floors, let's say, right? So let's think about the total number of drops that each drop of ball 1. So we first drop, let's say, ball 1 from floor 10, and then we drop ball 2 from 0 to 10, right? And it breaks at 9, right? So that equals 10 total drops, right? So then let's say it's not from 0. This is like imagine another scenario, right? So we're just seeing what happens to our numbers here. Let's say we drop ball 1 from 10 and then it breaks at 20, right? And then we drop ball 2 from every floor from 10 to 20, breaks at 19, right? So ball 1 drops 2 times and ball 2 drops 9 times for a total of 11 times. Again, we have a new set of balls. We go to 10, we go to 20, we go to 30, ball 1 breaks. So then we take ball 2 and we drop it from every floor from floor 20 to floor 30. And it breaks at 29. So in this case, ball 1 drops 3 times and ball 2 drops 9 times for a total of 12 times. So what's happening here? You can see that as the first ball has to skip more times, right? Our total drops grows. It grows by 1 each time. And actually, the amount of times ball 2 has to drop stays the same because we're dividing by the same number each time. So wherever ball 1 drops, we always are going to only ever at a maximum have to drop that second ball, the amount of floors we skipped, or 1 less, right? That's all it's ever going to be. So if we can somehow compensate for this growing number of total drops, right, we can maybe get our numbers down a bit. So it doesn't grow as the worst case grows. Maybe we can get it to even stay the same. Hint, hint, right? We're trying to maybe get it so that every single time we drop, no matter where in the building that first ball breaks, we're always going to only drop the ball some ideal number of times, right? So if it grows each time by 1, maybe instead of skipping the same number every single time, we can skip a different number every single time. So if it's growing by 1, we can compensate for that by making ball 2 drop 1 less each time, aka skipping 1 less floor each time with ball 1, right? So that way, as we add to our cases, we compensate for that ever-growing ball 1 number by making ball 2's number always be 1 less. So let's look at what happens, in a real example here, if we're decreasing the number of floors skipped with each drop of ball 1. So we start at floor 10, right? And ball 1 breaks. We then drop from 0 to 10 with ball 2, and it breaks at floor 9, right? So our total numbers are ball 1 drops 1 time, ball 2 drops 9 times, we've dropped 10 times total, right? Let's take the next example, right? So instead of skipping 10 and going to 20, we're going to skip 9. So we first drop it at floor 10, doesn't break. We then drop it at floor 19 instead of 20. It does break. We then drop the second ball from 10 to 18, right? So ball 1 has dropped 2 times, right? So it's still dropped an additional time, but ball 2 now drops 8 times only. So we've compensated for the fact that ball 1 had to drop an extra floor, and ball 2 now has to drop 1 less floor because we skipped 1 less floor each time. Let's see one more example. So let's say it didn't break at floor 19. So now we're going to skip 8 floors, right? We'll go to floor 27 with ball 1. It breaks there. And then we only have to go from floor 19 to floor 26 with ball 2. So ball 1 drops 3 times, but ball 2 only has to drop 7 times, etc., right? So our total number of drops is 10. That's great, right? We have totally just killed it. The interviewer is blown out of the water. However, there's a problem here, right? And the problem is that eventually, if we start at 10 and we decrease each time, that only gets us to, let's see, 10 minus 9 minus 8 minus 7, right? And I'm just adding those because that's the number of floors. We're going to get to only floor 55 before we have no more to decrease, because we always have to drop one, we always have to skip 1 floor, right? So that means we can't start with skipping 10 floors. We have to start with a higher number because we want to be able to decrease the number of floors every drop of ball 1 all the way until the top of the building, right? We want to continue to compensate for that until we actually have exhausted the entire building. Otherwise, we're right back to square one, because if we at 55 can only skip one floor, we're just going to be dropping every floor, right? And we're back to our naive approach, and that's not good. So how do we get this magic number, right? How do we find this number that we can, start from, that we will basically always be able to decrease the number of floors skipped with ball 1 until the very top? We want to minimize the number of floors we skip at the start to keep that second ball's numbers low, right? For example, we don't want to be skipping 20 the first time, because if ball 1 breaks on the 20th floor, then ball 2 will have to still skip 1 to 19 in the worst possible case. So we don't want to skip too many floors, or we're back to the binary search approach, which we know is not even as good as skipping 10 every time, right? But we also don't want to minimize it, because we want to be able to, we don't want to minimize it too much, because we need to be able to be decreasing all the way until the top, right? So this is kind of summarized here, that we want to minimize the number of floors we skip at the start, but still be able to decrease the number of floors skipped with each drop of ball 1. There's some magic number there. So if you see this equation, this is essentially summarizing what I just said, right? This 100 here has to do with the fact that we have 100 total floors in the building, right? This 1 is that before we get to 100, we want to be skipping 1 floor, right? That means we have perfectly led ourselves up to that state where at the top of the building, we've been able to decrease until we only have to skip 1, right? And then n is the number of floors we want to skip at the start, right? And then we want to decrease it each time. I hope that makes sense. It's a little bit, once you get it, but like it's a little hard to kind of reason about it first. But it's actually it's a simple equation, right? We're basically summing all the numbers from 1 to n, right? So we have to solve for n. Okay, easier said than done though, right? Because I don't know, how do you do that, right? So here is a great formula in case you don't have it in your back pocket. Here is a formula for quickly adding the consecutive numbers in a series, where n equals the number of terms in the series, aka the amount of floors skipped, right? That's each time that will be how many, that's how many times we are skipping at all with ball one. A1 is the first number in the series, so in our case, this would be 1. AN is the last number in the series, which is the same as n in this case, right? That would be the last number, or it would be the first for us, right? The first number of floors skipped. And S of n, Sn equals the sum of n numbers, right? That's the sum. Okay, so thank you, Carl Friedrich Gauss. He's a mathematician who figured this out at like age 8 or something. So, making the rest of us look bad kind of thing. Okay, so let's plug in our numbers here. We can then use the quadratic formula to solve for this. And the reason why we have to use the quadratic formula is because, n distributes, we're going to have to solve for n squared, right? So, ew, I hate that. But the answer to this equation, plugging in all of our numbers, will give us 13.651. It's not a round number, which means that at first we need to skip 13.651 floors. And then if we decrease by 1 each time, we will eventually only decrease by 1 before we get to 100, right? Because it's just going to be a series of first skipping this number, then skipping 12.65 whatever, then skipping 11.65 whatever, etc. We're obviously not going to skip by a non-integer number, so we're going to round up here, right? So we're going to round up to 14, and that is our magic number. Let's see it in action. Okay, so we drop ball 1 off of floor 14. We then drop ball 2, it breaks. We drop ball 2 from the first floor to the 14th floor. It breaks on 13, right? So ball 1 drops 1 time, ball 2 drops 13 times, total drops is 14 times. Cool. We skip now, let's say it didn't break at 14, right? We can skip from floor 14 to floor 27, which is skipping 13 floors, right? So that's 14 minus 1, so that's 13. So we get to 27. And ball 1 breaks, right? We then take ball 2, we drop it from every floor from 15 to 27, breaks at 26. Our total number of drops is 14 times, right? And so I hope that was kind of illustrative to you how we can, use math and logic to solve this problem that kind of is a difficult problem to solve. And the way we were able to solve it makes it, expandable, right? So now you can plug into this equation any number of floors, right? And you'll know that magic number that you have to skip from with the first ball. So obviously, some of you are probably thinking, I don't know how to solve for n in a, sum of a series and then use the quadratic formula in an interview on a whiteboard. And that's totally fine because obviously a lot of us can't just do that. So I think where, something to remember about this sort of problem is that it's actually not that hard to figure this out just by checking and guessing, or guessing and checking, I think is the saying. So you can go from, the binary approach, break it down to the 10 at a time approach, then break it down to the one less approach, right? And to find that magic number, you can try, what happens if I skip 10 every time? Oh, I only get to 55. What happens if I skip 11 each time? What if I skip 15 each time? Oh, I'm skipping a lot at the top, and then go back down to 14, right? And I personally, as someone who interviews candidates, I would accept that. And I would even maybe think, okay, that's absolutely reasonable because I don't need you to do the quadratic formula at your day-to-day job here as a software engineer. I think the point is that just because something is not obvious, or there might be a step that you may not get, does not mean that you won't answer that question in a way that demonstrates your skills, so that the interviewer can kind of really judge you based on like who you are as a problem solver, and less about how much knowledge you came with in your back pocket. So this is a really fun interview problem, I think, because it takes you a little bit out of that coding mentality and into the riddle solving mentality, which is what really brought me to this field in the first place. So if you guys like this, definitely let us know. We'll do a lot more like this. Otherwise, we'll see you next week for our usually programmed actual data structures and algorithms content. See you guys.